Right. So, and actually and sorting. Now, the last time when we were talking in on the on lectures, we mentioned then we mentioned heap and uh, how can we like what makes a heap and what is the maximum heap, what is the minimum heap, and then I also mentioned heap sort along the way, and then I mentioned also that we need to like finalize the part of the heap which is heapify, which means what happens when you are given an array or are given a heap that it's not satisfying the conditions of a maximum heap or a minimum heap, right? So you need to actually like make a process or make something which is called heapify. Okay. Now, once we are done with that, we're going to move into how to sort elements. We're going to talk about a little bit of a different topic. So in order just to complete the heap lecture, we need to cover just heapify, and then afterwards, I'm going to actually cover um, the sorting. So without further ado, if let me put even line rules. I think I was usually using a little bit larger grid lines here. So yeah. So imagine that we are having a heap that looks like this. So 15, 25. And right here, we're going to have 20. And then you have here 12 and 40. Okay. And this is your array. So we have 10, 20, 15, 12, 40, 25, 18. Okay. So this is the array. And this is how your heap layout looks like. So when we try to address and say, okay, so this is 1, 2, 3, 4, 5, 6, 7, right? We said that in the heap, we're going to use one based array for now because it's easier for calculations. And also we have mentioned that just as a reminder, we said that the left child of any element in a heap is going to be calculated as 2 times I, and the right child of any element in a heap will be 2 times I plus 1. And then we said that the parent is going to go into, like, you calculate the parent of any given node as floored I, or I divided by 2 floored. Okay. So if I look at 18, for example, and I say, what is the parent? The parent is going to be 7 divided by 2, which is 3.5. Floored is going to be 3. So here's your 15, which is correct, right? So we can actually double check each one of those, and you will figure out that this layout of the heap is correct. However, it doesn't satisfy one of the two conditions, which is either it's a minimum heap or a maximum heap. It's a complete and full binary tree though, which is totally okay. So right now we need to satisfy the final condition. Now, how can we heapify this? How can you make a heap out of this? So the first step which you're going to need to do to heapify, one, check the last element's children. Do they even exist? Right? So this is step 1. Check last elements, I think S like this, children. Okay, meaning that I will have to check, does this guy have any child? 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 Right? So I'm moving 18, 25, 40, 12. And if you actually look at this, I'm actually moving backwards in the array 18, 25, 40, 12. Right? So looking at this, this guy doesn't have a child, right? So you're actually like checking if there are any children. If there are not, you skip, right? So if there are none, you just simply check the next one. So 18 doesn't have it, skip. 25 doesn't have it, skip. 40 doesn't have it, skip. 12 doesn't have it, skip, right? Now what we do, we move on to the next element. So 18, 25, 40, 12, 15, right? So 15, I'm going to grab 15 right there. Does 15 have any children? So I actually like check. So because these guys might be actually pointing to null, for example, or index out of range. But let's say that they are null. That means that they are actually do not exist. So right now here, I'm just going to check, okay, who is the left child, which is 2 times I. So 2 times I is 6, which is 25, right? And then give me the right child, which is 2 times I plus 1. So 6 plus 1 is going to be 7, right? Which is 18. So I'm going to grab these two guys and compare them. Give me the largest of them, okay? So the first step is check the element's children. Second step, if there are children, compare, compare them and get the largest. The largest, because I'm making a maximum heap. If you would like to make a minimum heap, you get the minimum, right? So in our case, I would ask, okay, so in our case, let me write this down, 18. So let me write this down here, actually. 18, 25, 40, and 12, no children. In this case. Here, 15 has a child, has both of them, has actually 2 children. So has children. What we do, grab the children, compare them. So compare 25 and 18. Okay, 25 is larger than 18, right? Because I'm making a maximum heap. The next question here is 25 larger than 15? Yes, then you swap. Okay, so I'm going to swap 25 with 15. Okay, so what we do, we just simply say, okay, 25 goes away, and we put here 15, and 15 goes here 25. You swap this guy out, right now 15, 25. Trying to beautify as much as I can. Okay. Now we move on. You move on to the next element. So you actually finished with the 25, right? You were here because you were done with this, you were done with this, and you grab right now this guy, right? You were actually here. So right now we grab the next guy, which is 20, right? So step 3, continue. Continue to next element, right? And the next element will be 20. 20 has children, right? Compare the children. So we compare 12 and 40. Now, 40 is larger than 12, so this is the element which I'm going to pick. And then I'm going to ask, okay, is 40 larger than 20? It is, so we swap. So we swap. So 40 and 20 just swap. So here 40, 20, where are you? Am I? So 20 here. Sorry. I just reversed it in my head. So 20, there we go. And right here is going to be 40. And right here is going to be 20. Okay? We are all good. Now we move on. The next element. Actually, we always check, like you always check whether the children are okay at the end, but we know that there are no children anymore in the bottom. So we don't actually do the checking anymore, right? We just simply stop by the swapping. For example, when we come to the 10 right now, because 10 is right now coming up next, we continue. To the next element. And the next element is going to be 10, because it's actually like coming up next. And it's actually having a children as well. Has children. What we do, we compare. We compare the children. The children are 25 and 40. Who is the largest? So the largest is actually 40, right? So we swap it with 10. So right now here goes 10. Oh, hang on. Here goes 10. Here goes 40. Here goes 40. Here goes 10. And then we say, actually, like to complete the sentence here, compare. Oh, come on. Compare. 40, was it what? 40 and 25? And 40 was the largest, so we swap. And then right now we look at 10 and we have to check whether it has a children or not, because you cannot stop right there, because you never know if it has something in there. We actually never check because we know that there is nothing in there. So we never double checked again, right? But right now, since we have children all the time, starting from this level, we always have to check in the bottom. So step 5, check. I will call it if 10 is in place. I would say like we can actually like justify it in that way. Right? So each one of these checks, whenever we swap, we always check if it is in place, but because there are no children, we don't check if it's in place. But right now, these guys has it. And also this guy we could have actually said so as well. But in any case, when we swap, we always check, does this guy have any children? So we can actually check if it is in place. But right now, we are at this level. So if 10 is in place, so what we do, we grab the children, right? Who is the largest among these two? And the largest is 20. So we swap it. So 10 has children. compare 12 and I'll be with comma and 20. Now 20 is larger than 12, so we're gonna actually swap it with a 10. So right now 20 goes here. And 10 goes here. Okay, so right now this 10, 20. Okay, so we do the swapping and it's done. Right now you got an actual maximum heap. So you got a heap where when you calculate the indices, they are actually hunting, like they are actually being correctly laid out. Not only that, but you can also see that every parent node is larger than its children. So 20 is larger than 10 and 12, 25 is larger than 15 and 18, right? 40 is larger than 20 and 25. So this is a correctly maximum heap. If I start pulling one by one, like element by element correctly in a correct manner and adjust the heap again, we're gonna get a sorted array. The complexity of Heapify I don't know if you have noticed, but it's actually O of n. Because you are not having a double for loop here. All what you do is just looping over each and every element. And while you are moving, you never return back again. You just simply move in a linear fashion from one end to the other, non-stop. Right? There are no nested for loops in there. You just simply check, do you have children? If you do you actually, are you larger than or less than? And swap. All what you do is a swap, and all that is in one loop cycle, right? So that's why it's O of n. This is what Heapify is. Okay. Any questions regarding Heapify? None? I don't know where is the chat though.
No questions, no questions.
No questions, okay. All right, I don't know where the heck. Here it is actually. It's right there. Yeah, I need to remember that. Okay, fine. Okay, hopefully it's all clear. Now we move on to sorting. Okay. So let's talk about one of the infamous tools in computer science, at least, or in algorithms and data structures, which has been taught in universities everywhere. Everybody mentions it, called bubble sort. Okay. And bubble sort, just I will write it down here just for the sake of completeness. Is usually used as an educational tool. Okay. And not, let me just take this out. And not used in real world applications. Okay. Here's the interesting part. We always teach it. Like even when I was a student, a professor actually just brought it up and taught it. I think you will see it mentioned in the introduction to algorithms, the green book. I think I'm sure that it wasn't in the other book, data structures analysis with C. I'm sure it's not there. Usually people say, like when we try to tell students about algorithms and data structures, we introduce them to like trying to introduce them to the concepts, right? To make them understand how would you tell a computer to sort certain numbers. And then the people just simply like, I think bubble sort is a good like kind of introduction to, hey, you can think about it in that way. It is good. Is it good idea? Absolutely not. Is it correct? Yeah, it will work, but it is a horrendous algorithm and you shouldn't use it. But we usually use it or teach it so you could just simply have a sense of what it takes in order to tell a computer to sort. And then we, throughout the semester, we're going to actually look at multiple sorting algorithms. We're going to go from the extremely super slow, like the bubble sort, to the super duper fast algorithms, like the quick sorts, radix sorts, and their equivalents. Please understand that there are many sorting algorithms that has been invented, and many of them are good. Sometimes it depends on their use case. People use certain sorting algorithm over the other, and we're gonna see in the semester, God willing, later, how you could differentiate and which one you would choose best for your use case. But generally speaking, there are many out there, and we are just teaching a small subset. So whenever you actually explore on your own, you can actually figure out when you look at other sorting algorithms, you are familiar with the space. You can actually pick up something that is useful for you. Okay. All right. So bubble sort is actually very simple. It's nothing. There's nothing super scary or fancy about it. It's just imagine that you have an array, which is, for example, 2, 7, 4, 1, 5, and 3. Oh, sorry about that. Let me try to get this right. Let's say you have an array of numbers and you need to sort them. And sorting is important, right? So if you would like, for example, to sort products by what is the most expensive or the least expensive, right? You need, imagine that you are shopping on Amazon or any of the online shopping sites where you would like to give me the cheapest option or give me the most expensive option and or the most popular or the least popular and stuff like that, right? So what if you would like to do that? So you are actually getting usually ratings from for example, like from 1 star to 10 stars, for example, and you are getting products with 2, 7, 4, 1, 5, 3 ratings, for example, right? Usually, like in sorting, you will see us a lot of times we are using like zero-based arrays, sometimes one-based array, depends. But a lot in books, you can see them that are actually using zero-based arrays in sorting, like when they address the the elements in the array. So here's how bubble sorts work. You first step, you grab the first element, right? You compare it compare it to the next. Hang on, let me write this down correctly. Grab first element. Compare it to the next. And by the way, there are some people out there who are having fun with this stuff. Sometimes they make variations over bubble sort. I have seen somewhere online. It was kind of actually funny. Check them out when you can. Some people trying to speed it up for some reason. I cannot really remember right now, but there are many interesting variations people are trying to pull off just for fun rather than something serious. So yeah, anyway, so when you look at, we are trying to do ascending. Ascending means, so ascending means from smallest or lowest to largest. Descending means from largest to smallest. Okay, vocabulary here. So going up or going down. Okay. So even ascending a mountain, or descending a mountain, so that like depending on, like you can think of it that way. So grab the first element, compare it to the next one. So we grab 2 and 7. So 2 is actually less than 7, and I'm actually, again, I'm doing it from the I'm doing it in ascending, so from smallest to largest. So 2 is less than 7, so 2 stays in place. Okay, so 2 is less than 7, no swap. Okay, moving along. Compare 7 and 4, right? So 7 is larger than 4, right? So what we do, we swap. Okay, so we swap 7 and 4. So at the end of the day, you will end up with an array which is going to be 2, 4, 7, 1, 5, and 3. I'm just going to put commas right now because drawing boxes is actually time consuming for the time being. Okay, and you don't stop right there. This is the point of bubbling, because bubbles usually, like if you are pouring a cup of a gassed water or a sparkly water, as they say, you get the bubbles just moving up, right? In a cup. So it's exactly the same here. So I'm not done yet. So step 3, you compare 7 with compare 7 with in this case 7 and 1, right? And in fact 7 is larger than 1. So what we do, we swap, right? So you end up with 2, 4, 1, 7, 5, and 3. We didn't stop yet there, so we do it again. 4, you compare. Compare whom? 7 to 5. Because we know that the 7 didn't reach its place yet. So because if actually I don't swap, if the swapping didn't happen, that means it's sorted. We can think of it as the element or the array has been sorted, right? So we compare 7 and 5. 7 and 5, 7 is larger than 5. And so we actually swap. So right now you will end up with, let me see here, 2, 4, 1, 5, 7, and 3. 7 is still not sorted because it has been swapped. So we say 5, we compare 7 and 3. And 7 is still larger than 3. So we do a swap. So when we do a swap, we say, okay, it's going to be 2, 4, 1, 5, 3, and 7, right? And right there, when we actually try to check again for a comparison, 7 actually have reached till the end. So it actually has stopped right there, right? So 7, we can say 7 is sorted because it reached the end of the array. So 7 is sorted. So what do we do next? We shrink the array size, right? So it's going to be 6, shrink array size, meaning you don't check for the last sorted element, right? You don't check for the sorted element. Meaning as well, i.e., your array size dot size -1. When you are in the for loop, you just simply say, okay, it's going to be -1. You are always minimizing the checks. And you actually do it again because this has not been sorted yet, right? So you actually you go again. So you repeat the whole process. So you go number 7. You say, okay, grab 2. So compare 2 and 4, right? So you keep doing this, and then you say, okay, 2 is less than 4, 2 is sorted, no swapping, pick up 4, right? So no swap, you pick up 4. 8. So 4 and 1. 4 is actually larger than 1, then you swap, right? So you compare 4 and 1. 4 is larger than 1, we swap, right? And then at the end of the day, you will end up with an array, which is going to be 1, 2, 1, 4, 5, 3, and 7. Now, honestly, I can go on and on, but I think you already have seen, you can see already how this will go. 4 and 5 will actually not swap, and then you grab 5, and then you will ignore 4 for now, and then you grab 5, and then you're going to swap 5 and 3, right? And then when you compare, and then you reach the end because 7 will never be checked because we already said there's going to be array -1. So right now you end up with a lesser array and so on and so forth, right? So you are actually taking each one of these numbers and you are bubbling it up till the end of the array and seeing, if you are large, you just simply move up or you move forward. If you are small, you stay in your place or you go back, and so on. This is practically bubble sort. You just simply keep repeating the steps, one after one after one, until you reach the array size, which is going to be right here. You're going to be standing right here. And once you stand right there, you're going to end up with the 1, 2, 3, 4, 5, 7, I think, as a sorted array. Okay. The time complexity of this algorithm is O of n squared. Okay. It's a big O. The polynomial order is O of n squared, and it's a big O of n squared because it satisfies the big O definition of asymptotic notation, right? So this is the bubble sort, really short, really simple. You just simply grab every number. If it doesn't swap, you grab the next number afterwards, and then you carry on. And then you keep looping and looping until the array size just becomes 1, and this is it. You are having a sorted array. Nothing's fancy about this. We usually use this as a tool just to tell people, here's how it feels if you would like to sort an array of elements in a very, very naive way, very simple way. Does this make any sense? Do you have any questions regarding this? People?
No questions.
Okay. Carrying on then. Let me just minimize this. All right, let me grab another algorithm, which is also popular. I'm going to actually carry on without a break. and finish at least like the parts of the sorting which I wanted to mention here. Okay. So I will release you early. All right. Let's talk about insertion sort. Now, insertion sort is a popular one. It's also O of n squared. It's slightly more efficient in practical scenarios than bubble sort and selection sort. It proved its efficiency when people were benchmarking it. So let me actually write this down just to make this material complete. So insertion sort is slightly more efficient in practical scenarios than selection. Oh God, then selection and oh, and bubble sort. Okay, it proved its efficiency. And in fact, if you are in C#, if you are using array.sort, so you have a I think it's under the list of T. It's a method called sort. You will have it there. I think you have to pass in a lambda, which says how you would like to sort it, ascending or descending. But the fun part here is that according to Microsoft documentation, according to MSDN, if you are having like 10 elements, or actually maximum of 16 elements, it will use insertion sort. And if you are having more than 16 elements in the array, it will switch to quicksort. So it will use quicksort in case you are using having more elements in the array. However, if you are having 16 elements or less, it will use always insertion sort. Now, insertion sort is similar to how you can organize a deck of cards. So if you're playing cards, or you are, for example, organizing your pocket money or something like that, and then you would like to organize them based on their values, or you're organizing the cards based on their values or their suits, as they call it. So the aces, the spades, and whatever the rest are is whatever the rest are. If you would like to organize them, you basically grab from the pile and you put in your empty hand, right? And then you grab the next one and then you insert it immediately in the correct position. And then you grab the next element and then you try to insert it immediately again into the correct position, right? So you're always inserting like you are organizing playing cards in your hands, right? And I think even in the introduction to algorithms, the MIT Press, the green one, it has actually even a picture of, simulating this. They are showing you like a caricature of a guy holding in his hands a deck of cards and or a bunch of cards, trying to organize them. So it has even that illustration in, because it's actually the closest one to the real life, I think, like real life scenario. So how do we do that? So in insertion sort, we divide the array because you have in place sorting and not in place sorting, and we're going to talk about this later on in the semester, into two parts. You have the sorted part and the unsorted part. Okay. So, for example, how do we do that? How do we do that split, right? So imagine that you have an array that's looking like this. So 7, 2, 4, 1, 5, and 3. With an indices of obviously from 0 to 5, right? So in the first iteration, we consider the first element to be sorted. Okay? So this is the first thing you consider, right? So I'm going to say, okay, this guy is sorted, and it's actually in place. Okay, now what I'm going to do, because I'm actually going to need to divide the array into these two parts, and I don't know where to divide them. So I just simply said, okay, the first element is sorted. This is going to be the side where actually like, this is going to be the side where everything here is sorted, everything here is unsorted. Okay, so this is like, I consider said, okay, the first element is sorted, the rest are not sorted. Now we need to check against that, obviously. So we compare seven and 2, right? And then you see that 7 and 2, actually 7 is actually larger than 2 because we are trying to do ascending again. So ascending order. Okay. Hang on. Ascending order. So we're going to swap them. So I'm going to have at the end of the day an array that looks like this: 2, 7, 4, 1, 5, and 3. And then I will consider that this guy is actually sorted. This guy is not. Okay. Then we actually come up next, and then we pick up 4, right? We compare 4 to the 7. Is 4 actually larger than 7? No. Okay, we're gonna swap 4 and 7. But is actually 4 larger than 2? It isn't. So we will not swap it. So what we do, we can actually make that the 4 actually shift in place. So what we're gonna do here is okay, compare 7 and 2, we swapped, and I'm just trying to write for you the steps, hang on. And then compare 4 and 7. Then we're gonna actually swap them, right? So 7 is larger than 4. So we swap 7 and 4. However, we will not stop. We need to actually also try to test against the 2 later, but doesn't matter. So right now we say, because 2 is actually like rest, so 4 is going to be in place. So at the end of the day, we'll end up with an array of 2, 4, 7, right? And then 1, 5, and let me put some space here. And 3. This is sorted. This is unsorted, right? And if you look at it, 2, 4, 7 is sorted, 1, 5, 3 is not sorted, which is totally fine. Let's compare again. What do you compare? You will compare 1, and then you will start comparing it like you're going to actually compare it to every one of those. So compare 1 and 7, right? So compare 1, 7. Is 1 is actually less than 7? Yes, we're going to swap. Good. So we're going to actually swap it later. But then you compare again, is actually, so actually I can detail this. So we can say, okay, 2, 4, 1, 7. But then 1 is not in place because the if statement haven't failed yet, because 1 and 4, they are still 1 is less than 4, so you're gonna have to swap those guys. So at the end of the day, we'll end up with 2, 1, 4, and then 7, right? And then you're gonna have to ask the same question: is 1 and 2 are actually, is 2 is less than 1 or not? And then 2 is not less than 1, or actually 1 is less than 2 rather. So you're gonna say 1, 2, 4, and 7, right? So you're gonna have to do this insertion, like, right? So you're trying to find where it should go, and you are moving along the way. Once it reaches its position, you will end up with an array that is, this part is sorted, this part, sorry, hang on. Actually, it's going to be 5 and 3 right now. This part is not sorted, right? And then you pick up 5, and then you pick up, like, you pick up 5, and then you ask the same question. So is 5, so we compare. Five and 7, right? And 5 is less than 7, right? Or let me actually follow the pattern, which I always said it here. 7 is larger than 5. It is the same thing, obviously. Then we do the swapping, and obviously you're going to ask the same question, like, is, okay, 5 and 7 will be swapped, but do I need to swap it with 4? And obviously it isn't, because 5 is larger than 4, so you will end up with an array that looks like 1, 2, 4, 5, and 7. This is the sorted array, comma, 3 still not sorted, right? And then you grab the last element, and then you compare it with a 7, you compare it with 5, you compare it with 4, until you find its place, so you do the swapping. Obviously, you, all this time you are swapping, so you swap, you swap, you swap, right? So let's take it step by step here. I just simply jumped ahead. So 7 and 3, 7 is less than 3, larger than 3, sorry. So 3, 7, 5, 4, 2, 1. And then 3 is still not in place because we don't know yet. We didn't fail the check. So 5 is larger than 3, so we do the swap. So 5, 7, 3, 4, 2, 1. Then you do again the check. Still the if statement haven't failed yet. 4 is larger than 3, so 1, 2, 3, 4, 5, and 7. And then you do the check again, right? Because you need to know whether you fail or not. And then right here, 3 is larger than 2. It fails the check. You have the array sorted. Done. Okay, so this is insertion sort. Very simple. In practice, statistically, it has shown that it's actually performing better than bubble sort in terms of performance. I think also it was O of n squared, as far as I remember. Okay. This is actually one of the interesting things that it happens with algorithms, that you need to check. You need to check if the algorithm's working statistically well. So people are actually not throwing not only random numbers, or not only like, they are actually like, they're actually also throwing random numbers. But if you look at the arrays, usually when they are getting algorithms for sorting, when they are getting tested in terms of runtime, when they benchmark it, like when I showed you Visual Studio, the benchmarking tool, There are several ways of sorting an array. Sometimes I give an algorithm an already sorted array. So what happens if I give an algorithm an array that looks like this, and I tell it to sort it? Now the array, the algorithm will never know, so it has to run through this, right, in order to make sure it's actually been sorted, because you never know, you might actually end up with something like this, 0 at the end, right? And this array wasn't sorted. It was sorted all the way except the last element, right? So usually it does this check. Some of the arrays, like some of the algorithms, if you give them a sorted array, it will go through it fast, and it has a specific complexity, runtime complexity. Some arrays, if you give them reversed, so 6, 5, 4, 3, 2, 1, and then you ask the algorithm to sort this. Right now this is descending. Please do it ascending. It will have a certain another performance. It might perform better or worse than this. Some people give random numbers like what we have here, like they are jumbled up. They are not being sorted, just simply like noise. And people usually test the algorithms against these three things, like reversed arrays, sorted arrays, random noise to actually sort, I think, and that's pretty much it. And they grab the statistics and they see how the execution time has been faring. And at the end of the day, they say, okay, this algorithm statistically performs well in practice than others, based on such a statistical analysis. I'm just giving you the idea behind it. All right, hang on a second, give me a minute here. Just to check, maybe I can. All right, so let me actually have this one inserted as well, and then we call it a day. Selection sort. It shares some similarities with with insertion sort. Okay, we grab an element from the array. Oh God, forgot how to write. From the array. And then we actually we grab an element from an array, and depending on the sorting order, we compare it with the picked element with the maximum number possible. So this is the first step. So we grab an element from the array and compare it. Compare it with the minimum or maximum number possible. Okay, so int.max or int.min, for example, right? So if you would like to do ascending, so you compare with the largest number. If you would like to do descending, you compare with the minimum number. This is like your first start. And then you compare that number with the rest of the array, the one which you have picked, right? So for example, you say, okay, let's say I would like to compare I would like to make the array going from, let's say, from the smallest to the largest. So we are going ascending, right? We are going from smallest to largest. Assuming that you have an array that looks like this: 2, 7, 4, 1, 5, and 3. Okay? Assuming that you have an array that looks like this. So you say, okay, I would like to find the smallest number, right, in this array. So I will grab the maximum number, integer, right? And I will say, who's less than that maximum number? Let's say 1,000,000. I will just simply make a number right now and say 1,000,000. So I'll loop here and say, okay, for every element in this array, are you less than 1,000,000? Yes, you are. Then 2 is the smallest right now. Okay. So 2 is the smallest. And right now I have to compare the 2 against each one of these elements. I'll say, okay, who is smaller than 2? And then it happens to be that 1 is the smallest, right? So I'm moving just over every single element in the array, and 1 is the smallest. 1 is the smallest, great. I'm going to swap it with 2, right? So I'm just going to go ahead and have here 1, 7, 4, 2, 5, and 3. And right now, this guy is sorted. Do I have a highlight here? Great. This guy is sorted. Oh, okay. This is bad. This is very bad. Do we have another color? Can I do red? Yep, there we go. This guy is sorted. Okay, you don't touch that. Done. Then you actually like try to then you after you did the swap. Great. Now your array has been shrunk down. And then right now you search again for the smallest number in the array. Who is the next smallest? And then you say, aha, it's actually like 7, right? Because you are actually comparing to the int.minim or .max. And then you say, who's smaller than 7 right now? Smaller than 7, okay. 4 is not, 2 is, or actually 4 is. But you need to actually like swap with the smallest number possible in the array. So you are scanning the whole array and finding the smallest number possible. So 7 is less than 4, it is true. But is there anybody smaller than 4? 2 is actually smaller, like is the smallest. So we actually swap 2 with 7. So right now you're gonna get 1, 2, 4, 7, 5, and 3. So this guy has been sorted. This guy has been sorted. And right now what we do, we say, okay, who is the smallest element in this array? And then you will see that it's actually 3, right? You will swap it with 4. So it's going to be 1, 2, 3, 4, 7. Ah, hang on. 1, 2, 3, 7, 5, and 4, I think. So I actually didn't, hopefully I didn't mix it up. So these guys are sorted right now. Hopefully I didn't, 1, 2, 3, 7, 5, 4, yeah, okay, good. And then again, you're gonna scan, right? You need to scan the array. Are you actually sorted? Like, what is the smallest number in this array? So you say, okay, the smallest number in this array is 4. So you're gonna get 1, you swap actually 4 with the 7. So 1, 2, 3, 4, 5, and 7, right? And right now, this guy is sorted. This guy is sorted already from previous iteration, and this guy is sorted. Right now, what you're gonna do is you're gonna say, okay, who's the smallest element? 5. Do I need to swap it with anybody? Because it's actually right now it's actually in place. Comparing it with 7, it's actually in place. So right now it's been sorted. So this guy is sorted. And then 7 is only left, which is already in place. So this is also sorted. Okay. So this is basically what selection sort is all about. You just keep repeating this, like picking who is actually the smallest or who's actually the largest, depending on which direction of sorting you would like to go, either the smallest to largest or largest to smallest. Okay. Are there any questions regarding selection sort? No questions?
No questions.
Okay, I will actually stop recording here.